Hello everyone, hope you are doing well. I'm Reza, founder of the optimizationct.com. In this presentation, we are going to solve the linear programming model using three different methods. The Simplex algorithm, a well-known algorithm for linear programming problem. GAMS software, a well-known commercial software for optimization model, and online software provided by optimizationct.com. Let's get started. Today we are going to solve the linear programming model using the difference method, Simplex algorithm, the GAMS software, and the online solver provided by the website optimizationct.com. Here, what we are doing in this presentation, first we present the model and we then solve the problem manually using the Simplex algorithm. Then we will run the same model with the GAMS software, a well-known commercial software for optimization model. And finally, we will use the online solver from optimizationct to compare all three approaches. All right, this is the model. Let's look at the model we are solving here. It has two variables, x1 and x2, and a three constraint. x1 plus x2 is less than 100, x2 is less than 70, and x1 is greater than 20. x1 and x2 is non-negative. Before we jump into the solving the model, we need to convert the model into the standard form. The objective function should be in maximization form, so ours is minimization. So we multiply by -1, turning into here maximize z minus 2x1 minus x2. So we have the new objective function minus 2x1 minus x2. The constraint should be less than or equal, and our variable should be non-negative. In order to solve with the Simplex method, we need to add a variable as a slack for constraint number 1 and constraint number 2. So we have x1 plus x2 plus x3 is equal to 100. To make this inequality form to equality form, x2 plus x4 is equal to 70. We change this inequality form to this equality form. The third constant is greater than or equal to, so we introduce a slack variable x5 to rewrite this. x1 minus x5 is equal to 20. But here there is a catch. Every constraint needs the basic variable. So we have x3 and x4 is a basic variable for first constraint and a second constraint. But for the last constraint, we don't have the basic variable. To ensure the feasibility, now we add an artificial variable as a x6. We add the artificial variable to ensure the feasibility. Now we have the third constraint as here. We have x1 minus x5 plus x6 is equal to 20. Because we don't want to x6 in our final solution, we want this variable be 0 if possible. We use the big M method to derive it towards 0, which means modifying the objective function by minus mx6. So it's time to go to the Simplex table and start the Simplex methods. This is the Simplex table, the basic variable columns, track the chosen variable, the row number, row 0 for objective function, and row 1 and row 2 and 3 for constraint, column for coefficient of the variable in the equation and objective function, and right hand side, which is in the last column. The objective function is written here. So this is the objective function. We write here z plus 2x1 plus x2 plus mx6 is equal to 0. This is the objective function and place in row 0. So this is row 0. Oh, I prefer. Okay, row 0. It's better to type. Row 0, 1 plus 2 plus 1, 0, 0, 0, m, and 0. For the first constraint, x3 is a basic variable, and right here, x3 is the basic variable for row number 1, x4 is the basic variable for row number 2, and x6 is basic variable for row number 3. What is the coefficient? Is 0, 1, 1, 1, 0, 0, 0, and 100. For second constraint is 0, 0, 1, 0, 1, 0, 0, 70. And the third constraint is 0, 1, 0, 0, 0, minus 1, and plus 1, and 20. Here there's a point. x6 is a basic variable, but it still is in the objective function. To remove it from the objective function, we subtract row number 3. We subtract row number 3 times m from row number 0. For now, we have the x is a basic variable and 0 in the objective function. So what we have in the next table, by this operation, we still have z, x3, x4, and x6, 0, 1, 2, 3. So what is the value? 0, 1, 2 minus m. Why? Because we add 1, zap them, multiply minus m, and plus 2. So we have 2 minus m, plus 1, 0, 0, m, 0, and minus 20m. We have the same here, 0, 1, 1, 1, 0, 0, 0, 100, 2, 0, 0, 1, 0, 1, 0, 0, and 17, and last one, 0, 1, 0, 0, 0, minus 1, 1, and 20. So you can see here that x6 is the basic variable and only have 1 in this column for x6 variable column. Now we check the row 0. We can start with the simplex methods. If all coefficients of the non-basic variable are non-negative, we have reached optimality and stop. Here the coefficient of x1, x2, and x5 as a non-basic variable are 2 minus m, 1, and m respectively. We choose the most negative coefficient as an entering variable here, which is x1 is an entering variable. To select the leaving the variable, we use the ratio test. Divide right hand side by the positive value of the x1 column. 100 divided by 1 is 100. There is no deviation here, and 20 divided by 1 is 20. The smallest ratio determines the leaving the variable, and here is x6 exit. So This is x6. Now let's start with the pivoting and updating the table. Adjust the pivot row. So the pivot element here is 1. This is the pivot element. 1. This is the pivot element, which is already is. Zero out the rest of the x1 column using the row operation by multiplying row number 3 by m minus 2 and multiplying row number 3 by minus 1 and add to row number 1. So here we have 0. There is no operation here. By doing this, we can reach the next table, z x3, x4, and here x1, 0, 1, 2, 3. And what is the table here is 1 after the row operation for row number 0 and row number 1, 0, 1, 0, 0, 20, and minus 2. And the objective function is equal to 40. This is 0, 0, 1, 1, 0, 1, minus 1, and 80. 0, 0, 1, x3, 0, 1, 0, 0, and 17. And the last one, 0, 1, 0, 0, 0, minus 1, 1, and 20. Let's check the optimality. Here you can see that the all value in row 0 are non-negative, and which means we are done. And our optimal solution is x1 is equal to 20, x4 is equal to 17, x3 is equal to 100, x2, x5, and x6 is equal to 0, and z, which is objective function, is equal to 40. Okay, and that's all. We have solved the model manually. Now let's move to the GAMS solver. Next, we will solve the same model using the GAMS solver. This is the code we need to solve the last model using the GAMS. Define the variable. We have two variables, x1 and x2. Set the variable as non-negative. We just write a positive variable as a non-negative. Define the objective function and constraint. We have one objective function and 3 constraints as cons1, cons2, and cons3. We define the objective function and constraint using the GAMS syntax. Equal, E equal, it means equal. Equal, L equal is less than, and equal, G equal is greater than. We have the model here. We use the LP minimization syntax, which means because we are going to solve the minimized model, we need to write here as a minimization. And we use the display the optimal solution with display XL. We have the optimal value for variable and print it here. So let's go to the GAMS software. We run a new project. This is the code we prepared before. Okay, here, this is the code. The same code we see in the presentation, and we just run. Here, you can see that the x here, x1 is equal to 20, the level, x2 is equal to 0, and objective function is 40. And it takes is less than 1 second to solve. Okay, now let's see how our optimization online solver handle this problem. This is the main model we have. We add a variable x3 and x4 to the first two first variable, two first constraint number 1 and constraint number 2. By doing this, we have two constraints by equality. So for the third constraint, we subtract x5 to make this constraint as equality. In order to solve this problem by dual simplex methods, we need each constraint has a basic variable. x3 is a basic variable, x4 is basic variable because they are one in her or his constraint and zero other, but this is not right for third constraint. So we multiply the third constraint by -1. So we have this constraint x5 is a basic variable for this constraint. So it's time to solve this problem by dual simplex method. We have 5 variables, so n is equal to 5, and we have 3 constraints, so m is equal to 3. So let's go to the online server. This is the screen of the online server. You can see here, this is the website of optimizationct.com. Online server, dual simplex methods. This is the GUI for solving the online server dual simplex methods. And we have 5 constraints, 3 variable. This precision is like this, and this is the coefficient matrix. The first row for objective function, second for first constraint, third for second constraint, and finally for third constraint. And the first column is the right hand side of the model. So we just press the run, and you can see that we find the optimal solution. x1 is 20, x3 is 80, x4 is 70, other is 0, and objective function is -40 is equal to solution we use by the other methods like GAMS. This is the result. A big advantage of the online server over GAMS, no installation needed. Just run it from your browser. Thank you so much for watching us. If you have any question or need assistance, feel free to contact us via email or through our website contact form. Do not forget to subscribe our YouTube channel to stay updated with new videos. Goodbye.